Hi, this is actually a re-recording of the first part of our lecture today because I didn't have the right microphone on. So I just wanted to cover again how the problems on the quiz will be assessed. We will have a rubric. As you notice here, the rubric has the biggest part of the points allocated for expanding the hypothesis or the no and expanding the conclusions, the show. And the other points are minor. Notice that under standard cuts that we have full points of 35 off if you just have equations without any explanation of where the equations came from. So it's really important to line up that here's my hypothesis, here's what it means, here's what I'm trying to show, and here's what that means, and then deriving the logical steps to get there. I wanted to prove the conjecture. I gave you this to play around with, and I even told you it was false to get you to play around with it more and doubt it. But I wanted to prove this for you. It indeed is true that if you have D is the greatest common divisor of A and B, and if you have C as any other common divisor, then C must divide D. So the scratch work here is two pieces. First, we know that D is the greatest common divisor of A and B. And we also know the second part here between the if and the then, underlined in green, that C is a common divisor. Now, expanding this out, expanding the green part out, gives me that D divides A and D divides B, which gives me that D times S is equal to A and D times T is equal to B, and didn't write down that they're integers at this point. And the fact that C divides A and C divides B gives me that A is represented by C times X for some integer X, and B is represented by C times Y for some integer Y. So all my nuggets of information that I have are written below. And I have one more nugget of information. Whenever I have that D is the greatest common divisor of two integers, I also have the linear combination theorem that says that D can be expressed as A times U plus B times V for some integers U and V. So I've boxed off all the pieces of information that I can work with to arrive at my show. What I'm supposed to show is that D is a multiple of C, or that C divides D. That's my last sentence. And I'm going to put that last sentence up in the right corner of my slide so I don't use it. It's non-touchable. I'm not allowed to touch the show at all. I'm only allowed to work with the equations in purple and teal here. I'm not allowed to use the green that's up at the top. But if I know that I'm supposed to arrive at the green that's at the top, and the green that's at the top has a D and a C in the same equation. Now if I look at my purple equations, some of the equations have D in it and some of the equations have C in it, but neither one of the groups have both C and D in at the same time. And the teal equation is the same. It has a D in it and an A and a B, but it doesn't have a C in it. So looking at this, I'm trying to think of a way where I can use the information here to put D and C in the same equation. My brainstorm was to take the teal equation, D equals AU plus BV, and substitute the first, A equals CX and B equals CY in for the A and the B in the teal equation. So when I do that, I notice there's a C in both terms. And I'm able to factor the C out to the left, and now I have exactly that D can be expressed as a multiple of C. So my clean proof, we know by hypothesis that D is the greatest common divisor of A and B. So there's integers U and V such that D can be expressed as AU plus BV, which I refer to as a linear combination theorem. We also know that if there's another integer C that divides A and B, then there is going to be integers X and Y such that A equals C times X and B equals C times Y by definition of divisibility. If I substitute the first equations labeled 1 into the second equations labeled 2 for A and B, I get the equation D is equal to CXU plus CYV. By factoring at the C to the left, we get D is equal to C times XU plus YV. Since D is a multiple of C, by definition C divides D, and that completes the proof.